Hey everybody. What you're going to see in this is a clip from a bigger lesson on distance from a point to a line. What you're going to see is an example, a worked through example of one problem, how we come up with the distance from a point to a given line. I hope it helps you out. Good luck. I want you to take a look on your screen right now, and you'll see that on that screen, we have one problem. Find the distance from point A, negative 6, 7, to the line y equals 2x minus 1. Okay, if I were sitting down to deal with this problem, I would 100% of the time draw a picture. So, my suggestion to you, put on a quick sketch. Let's put on a quick set of axes, and the more accurate we can be, the better our diagram will be, the better our information will be, and therefore the better our outcome will be. What I'm saying is we could just throw on a sloppy line and say, hey, there's y equals 2x minus 1. Look, I was pretty accurate. It has a y-intercept of negative 1 and a slope of 2. Look, I'm rising to the right. Now, you might notice I don't really have a slope of 2. Like my slope looks closer to 1. That seemed to have like the same horizontal distance as what I have as my vertical one. And that inaccuracy is going to mean that my potential solution isn't going to match my picture that much. Now, it doesn't mean that my picture isn't helpful. It is, but it could be more helpful. So, my suggestion to you, when you go through and you build your sketch, take your time. I'm looking at that line, y equals 2x minus 1, and I say, okay, I have a y-intercept of negative 1. If I now want to have a slope of 2, then that means I have to make sure that my line is steeper than 1. And so what I might do then is I might take out my straight edge after estimating those two values. And now what I'm going to do is I'm going to try to draw my line through those values. When I do that, I now have a more accurate sketch for my line. And therefore, any conclusion that I might end up getting afterwards is going to be more accurate. Okay, there's my line. Now, I want to try to be as accurate as I can with my point. Well, negative 6, 7 means I have to go across 6 and up just a little bit more. Maybe there is my location of point A. And now, what that question's asking me for is to come up with the perpendicular distance. So, if I go to now try and draw on a perpendicular line segment, I'm not pulling out a protractor to do that. I'm just eyeballing it. But as I eyeball it, I want it to be, as much as I can, a perpendicular line segment. So I'm not now pulling out a protractor measuring. No, that means my sketch is too cumbersome. But I think if I just go on my eyes, then that's a pretty decent sketch. There's the situation that we've been asked to come up with. And you have been asked to come up with the length of the orange line segment. Okay, that's our job. Now, if you're looking for a challenge right away, then my suggestion to you would be pause the video and give it a shot. We'll come back and we'll see how well things go. Otherwise, you may want to kind of work together on this first one. Okay, what do I know in the problem? Well, first off, I know that the slope of that red line is 2. I can read it because it's in slope-intercept form. Well, if I also then know that my orange line has to be perpendicular to the red, then I know that any perpendicular slope to that has to be its negative reciprocal. So flip it, change the sign. Now, I am a big fan of trying to use as much notation and labels as possible. And so rather than just calling it a generic slope that's perpendicular, I'm going to actually use a line segment. I already have point A in green, but I don't have the other end point labeled. So I'm going to give it a label, and I'm going to call it B. That now allows me to state, rather than just a generic perpendicular, I can state that the slope and use subscript of AB is -1/2. Okay, there we go. Well, if I was able to go through now and figure out the length of AB, then I would need to know the position of both of those endpoints. I do know the position of A. I don't know the position of B. And so my job is to figure out what's the coordinates of point B. I do notice that point B is at the point of intersection between my orange and red lines. And hopefully we remember that to find the point of intersection means to solve a system. To solve a system means I need my two equations. Well, right now I have equation 1. It was given to me, my red line. I don't have equation 2, my orange line. I need to build it. There's my whole process. And we actually just walk through it in a backwards way. So I'm going to make an itemized list, and then I'm going to get rid of it for us, because that was us thinking about the problem backwards. Okay, here we go. For me to answer the question to find the distance, I need to know both endpoints. I know point A, I need to know point B. So I need to find B. Well, how can I find B? B is at the point of intersection between AB and the red line. That means I need to find a point of intersection. That means I need to solve a system. Well, for me to solve a system, that means I need my two equations, which means I need to find or build the equation of AB. Okay, what information do I need to build the equation of a line? I need slope and a point. And since I know that AB is perpendicular, I have both of those properties. Okay, all I'm going to do now is deal with the green, but backwards. If I find the equation of AB, I can then build the system and solve it. That'll give me the location of point B, and I can now find my distance. Okay, I'm getting rid of all of that stuff. Here we go. So the first thing I'm going to do is I'm going to build the equation of AB. And so to build that, I need point and a slope. Well, I'm going to sub my slope and point A into my slope coordinate formula. Now, I like using my slope coordinate formula other than y equals mx plus b, because then if I have fractions in my slope, I'm going to eliminate my fractions right away. That is, if I take a look at that equation, I'm going to put it in a useful form. That means I'm going to multiply out all my denominators. So I can multiply my 2 out to the right side, multiply my my x plus 6 up to the left side. So I'm going to multiply that by my -1. Now I can put this equation in a useful form. For me, that might be standard form. So there is my x and my y on the same side, my constant on the other. There we go. I like that. And that's all I needed, because there's equation 2. And if we look on the screen, you have equation 1 up in the top right side. Equation of the line was given. We've now built the equation for the orange line. If you want confirmation, rearrange that equation of a line into slope-intercept, and you can see your information. But I'm interested in finding point B. So to find point B, and I'm just going to come up here to the right, I need to solve my system. I can use substitution right away. Because equation 1 was given with y isolated, I could now sub 1 into 2. So I'm going to take equation 2. Wherever I see my y, I know I can replace it with what it's equal to. I can now solve that equation. And wow, do I get a nice, neat solution of 2. Well, there's my x value. I now need to sub x equals 2 back into one of my originals, and I'll sub that back into 1 because y is already isolated. That's going to get me a 4 minus 1, and I get a y value of 3. I just found that the location of B was at 2, 3. Now, I want to come back for a moment to something I said at the very beginning as I'm making this picture just a little smaller. I talked to you about the accuracy of your diagram. Because I took a little bit of care in my diagram, now when I found the coordinates of my point of intersection, they should be a little more accurate. And if we take a peek, you know what? That seems like a reasonable location. 2, 3, that's not too bad. Actually, I might chalk that up as that might be the best diagram I've ever drawn, at least in terms of accuracy. So, because I put in some time at the beginning, I get a little extra confirmation with my solution to my system. What I mean by that is, had I made a mechanical mistake in there and all of a sudden I found that the coordinates of point B were at -4, -2, you better bet that I am second guessing. I don't think I have the right B. Let me go back and look for a mistake. Okay. I've now come up with the value for B. I now need to come up with the length of the line segment. How far is it from A to B? So I am just going to come up on that right side. For me to go through now and find the length of AB, well, I can just use my Pythagorean theorem or my length of a line segment, however you want to choose that. On my diagram, I can see that I'm looking for the hypotenuse, so I've got to take my square root. My vertical side is going to be 7 minus 3, so it's 4 units long. So I need my 4 squared in my Pythagorean theorem. My horizontal side is going to be 6 units plus another 2, which gets me 8 units. And so I can just use Pythagorean theorem, or as I mentioned, you may have used your length of a line segment formula, you know, your x2 minus x1 squared plus your y2. That's totally fine. I can now calculate. And if I go to reduce that, then I get a 4 times a 20 and a 4 times a 5. I know that that whole thing will reduce to 4 root 5. There we go. That is a pretty big problem. And you can see that in that one problem, we use so many of our skills from our analytic geometry units. Dealing with perpendicular line segments, so therefore our slopes, building the equation of a line in orange, solving a system in blue, length of a line segment in green. That is a very typical problem for us to be able to go through. Okay, I want to talk about one more problem dealing with point to a line, but this one's going to be a little different.